Welcome to the lecture. You may recall that in the earlier lecture we had derived the ordinary least square estimator of regression coefficient vector beta as beta hat is equal to x transpose x whole inverse x transpose y. Under the model y is equal to x beta plus epsilon, assuming that epsilon follows a normal distribution with mean vector 0 and covariance matrix sigma square I. So, now we try to investigate the properties of beta hat, right. So, first we find out the estimation error, which is defined as say here beta hat minus beta. So, this becomes here x transpose x whole inverse x transpose y minus beta. Now, y is equal to x beta plus epsilon. So, we substitute it here and we obtain like this, and this is nothing but x transpose x whole inverse x transpose epsilon, because beta and beta get cancels out. So, you can see now here that when we try to take the expectations of beta hat minus beta, then because we have assumed that x is a non-stochastic matrix, so I can write this expectation as follows. And since we have assumed that expected value of epsilon is equal to null vector, so this comes out to be a null vector. Okay, so this clearly implies that beta hat is an unbiased estimator of beta. And remember, in case of simple linear regression model also we had shown that the least square estimator of intercept term beta 0 and slope parameter beta 1, they were also unbiased. So, this is again an extension of that result in the case of multiple linear regression model, right. Next we try to find out its covariance matrix. You may recall that in case of a simple linear regression model we had found the variances of beta 0 hat and beta 1 hat. We also found the covariance between beta 0 hat and beta 1 hat. Similarly, when we talk of the covariance matrix, we are moving one step further. And here in this case, we want to find out the covariance matrix of beta hat. Means earlier in case of simple linear regression model we had only two parameters beta 0 and beta 1 and their estimates as a beta 0 hat and beta 1 hat. But now we have k estimates beta 1 hat, beta 2 k hat, b beta k hat. So, when we are trying to talk about the covariance matrix, this covariance matrix has two types of elements, diagonal elements and say here off diagonal elements. The diagonal elements gives us an idea of the variances and off diagonal elements give us an idea of the covariances. So, for example, when I try to write down the variance covariance matrix of beta hat, this is nothing but expected value of beta hat minus beta hat minus beta transpose, and its structure will be something like this, that on the diagonal elements we will have variance of beta 1 hat, variance of beta 2 hat and so on, variance of beta k hat. And on the off diagonal elements, for example, here this will be a covariance between beta 1 hat and beta 2 hat up to here say covariance between beta 1 hat and beta k hat. Right, and similarly here covariance between beta 2 hat and beta k hat. Right. So, this is a symmetric matrix that we know. This is a symmetric matrix because covariance between xi and xj is the same as the covariance between xj and xi. So, and there is another concept here, that when we try to find out the trace of covariance matrix, matrix which is equal to here something like I goes from here 1 to k variance of here beta, or I should use j, beta j, right. So, this gives us an idea of the total variance, right. So, this is how we try to interpret the covariance matrix. So, let us now try to find out the covariance matrix of beta hat. So, covariance matrix of beta hat matrix beta hat, this is expressed as expected value of beta hat minus beta, beta hat minus beta transpose. And you may recall that here in this slide we already had obtained the expression for beta hat minus beta, right. So, I simply have to substitute it here and we obtain it like this, transpose epsilon, epsilon hat x, x transpose x whole inverse. Now, since we have assumed that x is a non-stochastic matrix, so I can take this this expectation operator inside and I can write like this. Now, we have assumed that expected value of epsilon epsilon transpose is nothing but the covariance matrix of epsilon, which is equal to sigma square I. So, I can write down here this thing as sigma square x transpose x whole inverse x transpose I x, x transpose x whole inverse. So, this is nothing but now sigma square x transpose x whole inverse. So, this is the covariance matrix of beta hat. The diagonal elements of this matrix will be indicating the variances of beta 1 hat, beta 2, beta k hat, and the off diagonal elements will be indicating the covariance between beta I hat and beta j hat. Okay. Now, we have another issue here now. This variance of beta hat is based on the population values. For example, it depends upon sigma square, and sigma square is a population value. So, in case if I need to know this covariance matrix on the basis of a given sample of data, we cannot obtain it here. And in order to know it, we need to estimate sigma square. Otherwise, this value is unknown to us. So, now in order to estimate the sigma square, we will try to follow the same philosophy that we have developed in the case of simple linear regression model, that we will start with sum of square due to residuals, and from there we will try to construct an estimator for sigma square. So, let us try to follow the same philosophy, and we recall that the residuals epsilon hat, which was defined as y minus y hat, we had defined as h bar y. And based on that, if I try to define the sum of squares due to residuals, this is nothing but I goes from 1 to n epsilon I hat whole square, which is nothing but epsilon hat transpose epsilon hat, and we have obtained epsilon hat as h bar y. So, I can write down here y bar h bar y, and since h bar is an idempotent matrix, so I can write down here as say y bar h bar y, right. There are some other forms also of sum of square due to residual. For example, I can also express sum of square due to residual as say y minus x beta hat transpose y minus x beta hat, and this if I try to open it, this will become y transpose y minus twice beta hat transpose y plus beta hat transpose x beta hat. Now, if you recall, we had obtained the normal equation as say here x transpose x beta hat is equal to x transpose y. So, if I try to use it, then this sum of square due to residual can be written as say y transpose y minus beta hat x transpose y, right. Similarly, there is another form SS residual. This was obtained earlier as a y transpose h bar y, and y is nothing but over x beta plus epsilon whole transpose h bar x beta plus epsilon. And if I try to open it, this will come out to be epsilon transpose h bar epsilon. And here actually we have used a result that h bar x, this is nothing but your I minus x, x transpose x whole inverse x transpose times x, and this is nothing x minus x, x transpose x whole inverse x transpose x. So, this will come out to be a null matrix. So, we have used this result, and using this thing we obtain here an alternative form of the sum of square due to residuals. Now, I am going to write down here a result, and using this result we are going to find out an estimator of sigma square, right. Say here z, which is something like z1, z2, zn. So, this is a n cross 1 vector, and suppose this follows a multivariate normal distribution with mean vector 0 and covariance matrix here I, identity matrix, then z transpose A z follows a chi-square distribution with degrees of freedom p if and only if A is an idempotent matrix of rank p. So, now using this result we try to obtain the estimator of sigma square. So, we just note down that we have assumed that epsilon is following a normal distribution with mean vector 0 and covariance matrix sigma square, and y is equal to x beta plus epsilon. So, expected value of y is same as x beta, and covariance matrix of y, this is covariance matrix of x beta plus epsilon, and this is same as the covariance matrix of epsilon, which is sigma square I. And y is a linear function of epsilon. So, I can write down that y is also following a multivariate normal distribution with mean vector x beta and covariance matrix sigma square I. So, now based on that I can write down that y transpose h bar y will follow a chi-square distribution with degrees of freedom trace of h bar, because h bar is an idempotent matrix. So, I can use the result, and based on that I can write down that the quadratic function y transpose h bar y will follow a chi-square distribution with the degrees of freedom which are equal to trace of h bar. And we may recall that we had found that trace of h bar is equal to n minus k. So, this is nothing but your chi-square distribution with n minus k degrees of freedom. And we also know that if there is some random variable here which is following a chi-square distribution, then the expectation of that random variable is same as the degrees of freedom, and its variance is same as the twice of degrees of freedom. So, using this result I can write down expected value of y transpose h bar y is equal to n minus k sigma square, and hence y transpose h bar y over n minus k is equal to sigma square, and this implies that sigma square hat is equal to y transpose h bar y over n minus k. This is, and This is actually nothing but sum of square due to residual divided by n minus k, and we define it here as a MS res, which means mean sum of squares due to residual. Right. And so this turns out to be an unbiased estimator of sigma square. So we have now obtained the least square estimator of the regression coefficient vector beta 1 hat, beta 2 hat, beta k hat, and we also have obtained now an unbiased estimator of sigma square. So now we have obtained the estimates of all the model parameters. Now there is another question, that how do we ensure that the estimate of regression coefficient vector which we have obtained through the principle of least square as beta hat is equal to x transpose x whole inverse x transpose y, is it a good estimator? So for that we have a theorem what we call as GaussMarkov Theorem, and this theorem states that the ordinary least squares estimator beta hat is equal to x transpose x whole inverse x transpose y is the best linear unbiased estimator of beta. Well, we are skipping the proof of this theorem, but we would like to explain what does this theorem is trying to say. This theorem is trying to say that if we have a parameter beta, and suppose there are more than one estimator available for estimating beta. Out of those estimator, first we try to identify that which of them are linear estimator, and from the group of or from the class of those linear estimator, then we try to identify that which of the estimators are unbiased estimator of beta. Now those estimator which are linear and which are unbiased estimator of beta, if we try to find out the variances of those estimator, then the estimator based on ordinary least square estimator will have the minimum variance. So the ordinary least square estimator are having the minimum variance in the class of linear and unbiased estimator, and that is the message what is given by the Gauss-Markov theorem. Now after this our next objective is that we demonstrate how to estimate the parameters using the method of maximum likelihood. So method of maximum likelihood we have used in estimating beta 0 and beta 1 in case of simple linear regression model. Almost on the same lines we can demonstrate here that how to estimate the regression coefficient vector and sigma square, right. So in the model y equal to x beta plus epsilon, we have assumed that epsilons are following a multivariate normal distribution with mean vector 0 and covariance matrix sigma square I, and we know that the probability density function of epsilon I is 1 over sigma root 2 pi exponential of minus 1 over 2 sigma square epsilon I square, and I goes from here 1 to here n. Now I can write down the likelihood function. We had defined the likelihood function in the case of simple linear regression model as the joint density function of all the random variables. So, in our case the likelihood function is nothing but the joint probability density function of epsilon 1, epsilon 2, epsilon n. So, in our case we denote this likelihood function as say L, which is a function of betas, and sigma square, which is joint density function x1 epsilon 1, epsilon 2, epsilon n. And since we have assumed the independence, so I can write down that this is nothing but product of f of epsilon i's, right, because epsilon i's are independent, right. So, this becomes here nothing but 1 over 2 pi sigma square raised to the power of here n by 2 exponential of minus 1 over 2 sigma square summation I goes from 1 to n epsilon I square, right. And the same thing can be written 2 pi 1 upon 2 pi sigma square power of n by 2 exponential of minus 1 over 2 sigma square epsilon transpose epsilon. And this can further be expressed as 1 upon 2 pi sigma square is power of n by 2 minus 1 over 2 sigma square y minus x beta transpose y minus x beta, right. Okay. So, now since we know that the log transformation is monotonic and it is easier to handle the log of L beta square rather than the likelihood function. So, we try to take the log transformation and we try to define here say L star, which is natural log of L beta sigma square, and this is nothing but minus 1 minus n by 2 log of 2 pi sigma square minus 1 over 2 sigma square y minus x beta hat y minus x beta, right. Now, I will simply use the principle of maxima and minima to obtain the value of beta and sigma square such that this likelihood function is maximized, right. Okay. So, we obtain the normal equations by partially differentiating L star with respect to beta and with respect to sigma square. We obtain here 1 over 2 sigma square twice of x transpose y minus x beta, and here we obtain minus n over 2 sigma square plus 1 over 2 sigma to the power of here 4 y minus x beta transpose y minus x beta, right. And we put them equal to 0. So, now we have here two likelihood equation 1 and say 2. So, first we try to use here the equation number 1. We obtain here that x transpose y minus x beta is equal to a null vector. So, I can, or this can be written as x transpose x beta is equal to x transpose y, and when I try to pre-multiply by x transpose x whole inverse, we obtain here x transpose x whole inverse x transpose x beta is equal to x transpose x whole inverse x transpose y. So, we obtain here beta is equal to x transpose x whole inverse x transpose y, and this we denote as beta tilde, right. And similarly, when I try to use the second equation, we obtain the value of sigma square is equal to 1 over n y minus x beta transpose y minus x beta. So, obviously, this cannot be obtained because beta here is unknown. So, in this case what we do that we replace beta by beta tilde, and this gives us a maximum likelihood estimator of sigma square like this. Well, these are the maximum likelihood estimators. We still need to show that the value of beta equal to beta tilde and sigma square equal to sigma square tilde, they really maximize the likelihood. So, in order to show whether beta equal to beta tilde and sigma square equal to sigma square tilde are maximizing the likelihood function, we try to obtain the second order derivative. Second order partial derivative with respect to beta, with respect to sigma square, and with respect to beta and with respect to sigma square. And we obtain this expression as a minus 1 over sigma square x transpose x, and this expression is n over 2 sigma is power of 4 over 1 upon sigma is power of 6 y minus x beta transpose y minus x beta, and this is 1 over sigma is power of here 4 x transpose y minus x beta. And then I can write down the Hessian matrix as partial derivatives of L star with respect to beta square, partial derivative of L star with respect to beta and sigma square, and partial derivative of L star with respect to sigma square, and so on, d sigma d beta. And then I try to obtain its value at beta equal to beta tilde and sigma square equal to sigma square tilde. And this Hessian matrix comes out to be negative definite. At beta equal to beta tilde and sigma square is equal to sigma square tilde. So, this implies that beta tilde and sigma square tilde are maximizing the likelihood function. Right. So, now I can say here that beta tilde is equal to x transpose x whole inverse x transpose y is the maximum likelihood estimator of beta, and sigma square tilde, which is 1 over n y minus x beta tilde transpose y minus x beta tilde, is the MLE of maximum likelihood estimator of sigma square. Right. One thing what you have to notice here, that the ordinary least square estimator and maximum likelihood estimator of beta are the same, whereas ordinary least square estimator and MLE and maximum likelihood estimator of sigma square are different. The difference lies in the denominator. In case of ordinary least square estimator, we had seen that the denominator was 1 over n minus k y minus x beta hat, and in this case and in the case of maximum likelihood estimator, the denominator here is n, and that is obvious, means maximum likelihood estimates have established property that they have the minimum variance. So, whenever we are trying to divide the quantity y minus x beta tilde transpose y minus x beta tilde by n, we are going to get a lower variance. So, now we stop here, and in the next turn we will try to explore some more aspects. Till then, goodbye.